Welcome to the DDPS seminar, everyone. It is an honor to host Paul Atzberger, who is currently a professor at the Department of Mathematics of University of California, Santa Barbara.
All right, thank you. I'd like to thank the organizers for this opportunity to talk today. I thought I would share a little bit of work that we've been doing on leveraging recent developments in generative modeling, in particular machine learning approaches that have been emerging, especially in the deep learning community, for the purposes of developing multi-scale models, reductions, and other types of representations for nonlinear dynamical systems of larger scientific simulations, so fluid mechanics, materials modeling, and so on. So I'm going to talk about a rather sort of small piece of the work that we're doing, and this is relatively recent work, and I'd be very happy to continue discussions offline about various directions and applications. So just to set a little bit the context in which I'm motivated in developing these data-driven methods is what we're really after are ways that we can utilize observations, either taken from experiment or higher fidelity computational simulations, and really use data-driven perspectives to essentially learn representations which we can use as a simulator, either to predict future behaviors of the system, or in the context of a much larger calculation where perhaps the part of the model that we're interested in replacing is very computationally expensive to compute at a high level of detail, but for the purposes of larger scale phenomena that we're interested in, a much sort of coarsened or simplified model would potentially do the trick, but it might be very difficult to arrive at that through kind of traditional asymptotic techniques. And so what I'm also interested in is in doing this in the context not only of deterministic systems, but stochastic systems, and that's primarily what I'll talk about today. I feel like, again, to build some context, I need to say a little bit about techniques that are out there and have been successfully applied for this type of problem, so I can kind of compare a little bit and contrast some of the objectives of the techniques that we're developing. And so there's been a lot of work done over the years, of course, in data-driven modeling of dynamics. Probably one of the most notable one is this proper orthogonal decomposition. This is essentially a form of principal component analysis, where the basic strategy to build up your dynamical model, here I'm just showing a fluid mechanics model on the upper right, would be to look at the modes in the system essentially that vary the most. So essentially you would take your flow field, create this very high dimensional point cloud, and effectively you're doing principal component on that. A really nice development in the direction of incorporating dynamics within this kind of linear frameworks is the dynamic mode decomposition introduced by Schmid in 2010, and lots of developments by various groups and communities, including Brunto and Kutz, in various directions. And again, this is a linear based model. Again, there's a lot of advantages of having linear-based models. They're much more straightforward to build theory for, and potentially computationally more efficient than training, let's say, deep neural networks. And so the basic idea in things like dynamic mode decomposition is you're basically going to take dynamical information into account by saying, well, which modes are sort of most indicative of that prediction of what's going to happen in the future over some set of snapshots. So you're basically looking for, again, the sort of best linear model and kind of the best basis in order to try to align your linear predictor with the underlying data observations. There's also been really nice work done on using symbolic approaches, essentially L1 regression, things like the lasso combined with these symbolic dictionaries, and that's a way that you can overcome some of the issues that I mentioned of these previous linear models. And again, lots of successes and nice applications of these techniques. But this has the drawback that you do need a sufficiently expressive library so that you kind of have coverage over the space of potential dynamic representations that are relevant for your system. So my main point in mentioning these approaches, I just want to give kind of some context of what's out there, and it kind of just helps set a little bit the overarching environment in which we're trying to develop these data-driven techniques. I'm also going to incorporate noise, so there'll also be a generative component that I'll be talking about in detail. And so the objective is try to not just recapitulate the behavior that you're seeing in the training set, but really learn your intrinsic model so that you can make either longer-term predictions, or ideally in the context of a lot of these scientific computing applications, be able to replace one of your more expensive models with one that's much cheaper but a long time simulator. And so that poses a lot of challenges from the data-driven modeling perspective, because depending on how you go about this, your model class might not have certain intrinsic properties that we're used to when we design into our numerical methods, such as things like stability, which obviously would be very important for long-time prediction. Also, another challenge is incorporating prior knowledge to the extent that we can. We often know a lot about, the physics of the system or other mathematical structure in the system. And so we'd also like ways of including that as inductive biases in our data-driven methods. So I'll talk a little bit about where I think there are opportunities to do that as well in some of these nonlinear approximation approaches. As I said, these developments in the neural networks community, in particular generative models, and I'll kind of put it in a little bit larger probabilistic context. And then there's a lot of interesting directions I think that this could be pursued for a lot of the applications that I showed on the previous slides, but going beyond, again, the sort of linear approximations to then incorporate various types of nonlinear approximation classes. So as two motivating examples, and I'll come back and I'll give some results for these, one of which is basically systems identification or extracting state information, which is important in many different problems, including things like control. And the objective here basically is to learn key parameters from observations of the dynamics. These things go by many different names depending on the community. And now what we're trying to utilize here, as I showed in the upper right, just a little animation. If I'm trying to learn, for example, in this Ornstein-Uhlenbeck process, you can think of it intuitively from the mechanics point of view as a bead spring system where I'm trying to learn simultaneously the stiffness, the damping, and the temperature of the system. What we want to do is somehow probe the dynamics in a way that would be indicative of those different properties. So there's going to be an interesting challenge whenever you're trying to estimate a model from the dynamics that you have to be careful basically that you're probing the dynamics on the appropriate timescales and that you have sufficient coverage over the response range that would be sensitive to those particular parameters. But the overall objective here is to try to learn dynamical representations from observations, sample trajectories. Also in reductions and coarse graining, I'll show an example where we're trying to learn essentially unknown force laws, and so how that can be done again from this generative perspective. In this case, this would be a non-parametric estimation problem where we want to learn an unknown force law, for example, in something like Langevin dynamics. And so problems analogous to this come up in a lot of different contexts in developing, again, reductions so that you can simulate things on larger timescales to overcome, for example, sources of stiffness, or in coarse grain modeling, of course, which is very popular, for example, in the material sciences community. So some of the interesting things that you could potentially do if you had good nonlinear estimation methods is, not have to handcraft your estimators for things like the force law. So one of the common ways you might try to go about doing this is to use something like maximum likelihood estimation. But of course, the immediate challenge you run into in the setting of these dynamic representations is that you have to specify likelihood functions. You have to compute those potentially on very high dimensional probability spaces. And so I'm going to show some alternatives to that approach. All right, so I just wanted to give some of the kind of key motivations here in context of where we're trying to develop these techniques, just to give a sort of overview of some of the issues that arise. And I think there's a lot of potentially interesting ways, again, to leverage a lot of the recent developments in the machine learning community. In the case of stochastic dynamics, in some sense, we're trying to learn an entire ensemble. And so there'll be some interesting issues that arise there, given the roles that noise plays in stochastic phenomena. And then, of course, as I said before, we'd like to do all of this to obtain robust representations that are stable for the purposes of either long-time prediction or simulation. All right, so I think I've said enough at the sort of the high level, and I'll start getting into some of the more details of the techniques that we're going to leverage and to further develop. So if you're not familiar with generative adversarial networks, I'm just going to go through really quick what these techniques are. These are recent developments in the machine learning community, closely related to generative modeling statistics. And so what I'm going to do is just go through perspective on generative adversarial networks. This is basically a way for us to train a simulator or an implicit generative model. That is this function that I'm showing here, which is G of Z. And G of Z basically has some noise source. And what it's going to do is generate a sort of collection of samples. And the objective here is to take our training data and take our implicit generator and have some way of comparing the samples that we get from the the training set with the samples that were produced by the generator. Now, as I mentioned before, one way that this has traditionally been done, if you know a lot analytically about the generator, is you could use things like maximum likelihood estimation. But if you do that, right, this requires the specification of likelihood functions, requires you to go and perform those calculations during the training loop, which could potentially be quite challenging. The appeal of doing this adversarial training approach is, instead of relying on a sort of pre-specified likelihood function, what we're going to do is simultaneously train another model. This could potentially as well be a neural network, but can be taken from any model class you like, and I'll show a little bit about that in a minute. And basically, the job of this discriminator is to characterize how closely the samples that were produced by the generator differ. And so the discriminator you can think of as playing a role analogous to a classifier. And if I have this collection of samples, its job is to say, well, did those samples come from the training set or the generator? If it can distinguish that readily, then your generator needs to be improved. You could think of this as kind of like a two-player game, where if I had a classifier loss, for example, the discriminators would be aiming to minimize the loss, while the generator would be aiming to maximize that loss for the discriminator. And so by making different choices of the discriminator, we can actually realize different divergences in metrics for comparing the empirical measures of the samples of generator with that of the training data distribution. All right, so that's a quick overview of GANs. So you have a generator G. What's different from some of the other modeling approaches is we're not actually going to write down ever the probability distribution or measure directly. We're simply going to have an algorithm that generates from some random input samples. And then we're going to tune essentially that algorithm so that it produces high quality samples that agree with the training set. And then the discriminator, the simplest case would be a binary classifier, which I'll use for illustration, and then I'll show how we can extend that for the purposes of these learning of dynamics. If it were a binary classifier, basically the idea would be it would give us a number, maybe between 0 and 1, telling us the probability that it thinks it was produced by the data distribution versus produced by the implicit generator. So I'm going to write these probability densities down for the purposes of having a theoretical perspective, but in practice, you're only going to be working with samples from G, and D will only be operating on sample sets from G and the training set. So basically, you can think about it a little bit like it's like a little game where G is kind of acting like a counterfeiter. D is kind of a classifier, seeing whether this is real or fake, and your job is to create such good samples again that the discriminator can't tell. All right, and we'll see how that plays out mathematically in a little bit, and that'll inform our choices for the discriminator model classes. All right, so the way that we're going to typically play this game is what we'll do is we'll have a synthetic data set, which is a mixture of samples that are taken from the generator, samples that are taken from the training set, and those get mixed together, and we put label 1 on everything from the training set, and we put label 0 on everything from the implicit generator. And now we can leverage results from the classification theory to create a loss function for the discriminator model D. And so the score of the discriminator is basically going to be, the 0-1 loss for assigning the correct labels to those sample points. Now, if we look at it from point of view of, let's say, the Bayesian classifier, you can see that if D of X is interpreted as a probability, the ideal way to try to classify would be for D to estimate the probability that the label is 1 given that sample point. Because you could have that both the generator and the data distribution produce the exact same sample. Of course, in practice, there'll be a little bit of smoothness that needs to come into the problem, where you want this for X's that are close, that they have the appropriate probability assigned. And then 1 minus D is basically the probability that the label Y was assigned. So of course, the Bayes classifier would be to just take the argmax of that conditional probability. What we're basically trying to do is develop an algorithm to find effectively that Bayesian classifier for this mixed synthetic data set, which is acting for the classifier's point of view as effectively like a training set. But I call it synthetic training or synthetic label data just to distinguish the original data from this synthetic one that we're using for the purposes of the GANs. And so if we mix together 1/2 probability, the things from the generator, and 1/2 probability from the original training data, this would be the distribution that we're training the discriminator over. And the Bayes classifier actually can be worked out analytically to be this. So it'll essentially just be the probability of the data distribution generating that sample over the sum of the probabilities of the data and the model distributions having generated that probability. So you can see that the optimal, if we were to actually perform all of our optimization perfectly, the best discriminator, the one that would minimize the loss, the 0-1 loss, would be given by this analytic expression here. Of course, in practice, we don't get that, but some interesting outcomes you see is that if I had that the data distribution and the model distribution lined up perfectly, I would have that this d of x is 1/2. And that kind of means that the discriminator was maximally confused, didn't know whether it should assign a label of 0 or 1 is the way you can intuitively interpret that. So if you now go and you get a little more mathematical about what we're actually computing here, we have this objective function. The theta d here are the parameters for the model class of the discriminator, and the theta g here are the parameters of the model class of the generator. What we're basically minimizing in the loss function is this expectation of the log label probability here. This is the usual 0-1 loss. This is what that amounts to. And now if you break it down for what we have for the synthetic data set, you'll see that it breaks into these two parts. And this is the typical loss that would be used for discriminator in something like GANs. Now we're going to see there's some drawbacks to this, and I'm going to have to reformulate the GANs for the purposes of learning these stochastic systems, but I wanted to kind of show you the sort of standard and original formulation before I do those modifications. So at the end of the day, what you'd be doing is trying to find an argmin of this objective function to get your discriminator. Basically, you're trying to have the best classifier possible given that synthetic data set. And then the generator's job is basically to try to mess up the discriminator's ability to achieve a low loss. In other words, make your sample so good looking that the discriminator really can't tell between the samples it's producing and those of the data distribution. So that's sort of the underlying strategy, and this is how it plays out mathematically. I've used a little bit of a modified objective here just to avoid some issues with vanishing gradients, but nonetheless, that's what this objective is ultimately achieving when you argmax it with respect to the generator's parameters. You know, very prone to oscillations if you use kind of this alternative descent ascent. But anyway, I just wanted to mention what the typical training objective is, and we're going to use some analytic techniques to work around that issue of oscillations that arises. I'm just showing an example with learning something which is relatively simple, which is a Gaussian. But the key point I really want to make here is you don't know in advance typically what is a good noise source. And so the real sort of issue here is the noise source I took to be a uniform distribution. I want to compute something like a Gaussian. You'll see that even trying to train on a model that's this simple, GANs runs into some, and you see immediately that you get a lot of oscillations during training. And really what's going on here is it's very difficult often in GANs to resolve the tails, especially if you don't have a decaying noise source. But you know, you could replace this obviously with a Gaussian noise source, and you'd very readily be able to learn the model. But this is really the scenario that you often encounter in practice: is the noise source often needs to undergo some pretty radical transformations in order to realize the target probability distribution. So we want to be very careful about the objectives that we're using to train the GANs. And there's this issue of oscillations if we use simply this relaxation, this gradient descent for discriminator, gradient ascent for the generators. And so what we've done is introduced a way to modify the standard formulation of GANs to incorporate some additional features to deal with some of those issues related to oscillations, to deal with some of the issues related to the noise that I mentioned, as well as the high dimensionality. And so we refer to this as stochastic dynamic GANs. So the basic objective, again, is to learn an implicit generator, a generative model, G of Z here. X would now be the trajectories, and we'd like to be, again, sample-based. So we'll use this setup with discriminators. Now, if you observe stochastic trajectories, the reason why I can't just use the standard GANs formulation is the dynamic trajectories would be very, very high dimensional random variables. And so you can imagine it being very prone to not having good sample coverage. In fact, if you do the standard GANs formulation that I showed before, you can show that that loss that you ultimately get is based on Kullback-Leibler divergence, and you have to be very careful about probability distributions being absolutely continuous with respect to the other. And so as a consequence, getting coverage in the sample space would be quite challenging when you go to very high dimensions. And so what we're going to do is we're going to use the probabilistic structure that we often know in advance about dynamical systems. For example, if we're looking at something like Langevin dynamics, we know that the new state is likely to depend on some previous number of states, in that case, 2 states. And so what I'm going to do is I'm going to develop my learning methods over the class of general m-step stochastic integrators. And that's going to be the model class, essentially, for my implicit generators. And by doing that, I can sort of build in various inductive biases, including learning within, let's say, the framework of numerical methods, which are known to be stable, at least for sufficiently small time steps. And basically from that, I can then learn my representations in a way where I have a viable candidate simulator in hand. So from the modeling point of view or probabilistic point of view, you can think about us learning over essentially probabilistic graphical models, where we're going to allow for state K there to be a dependence on the previous M steps. Okay, so that's going to be the basic way that we deal with some of these high dimensionality issues. And then I'll talk about how that probabilistic structure not only can be used for the full trajectory, but we also can look at trajectory fragments as the signatures that we use in the discriminator to drive the generator towards the data distribution samples. So the key idea here is really we want to be completely sample based so we can avoid having to specify likelihood functions. So throughout there will be no likelihood functions. So you can think about these as being methods that are alternatives to maximum likelihood estimation. All right, so the learned representations I'm going to use as my model class stochastic m-step methods. So just to get some notation specified, this is just saying that coding this probabilistic graphical structure I'm showing here on the right, we'll have that state j depends on the previous m states. You can think of psi j minus 1 as the update from time step or step j minus 1 to j. Omega j here will be the sample point because we're dealing with a stochastic process. And then the p here will be whatever parameters we have of the system. So these could be your weights of neural networks, or they could be parameters of the physical system that you'd like to learn from your trajectory observations. I'll also allow the parameters to influence the initial conditions, or you could think about that as coming from some ensemble for the initial conditions of the system. All right, so that's the basic setup in the model class that we're going to use for our implicit generators. And this provides all kinds of ways to incorporate prior knowledge, physical principles. We can sort of design into this update all kinds of features. I'm going to replace the standard kind of Jensen-Shannon divergence approach of the original GANs formulation with another approach that's kernel-based, and that will also provide some other ways to incorporate inductive biases. And then, as I said before, this encodes essentially these probabilistic dependencies. So we're not learning over the general space of, R n times D random variables. We're really learning over this class of graphical models. Now, once you do that, there's also a way to introduce different training protocols. Realize you can train this quite effectively, not just using the full trajectory data, but also using things like conditional distributions or even just marginal distributions. And this allows for potentially big reductions in the number of dimensions you have to deal with during the training process because you can utilize trajectory fragments. And so I'll show some results there, as well as downsampling by using different timescales, tau. So the overall objective then is going to be to develop appropriate discriminators and critics for this sort of dynamic scenario. Currently, what we're developing are methods within the context of generalized moment methods or maximum mean discrepancy. And we found in practice this seems to lead to some nice results with respect to avoiding some of those oscillations like I showed you in the standard GANs formulation. All right, so those 3 training protocols, I'll just say a little bit about them briefly because they'll kind of come back when I develop some of the algorithms. So in the full trajectory case, essentially what we're going to think of as the implicit generators distribution would just be essentially the sequence of snapshots of the dynamic trajectory. And of course, that's going to be very high dimensional, and that's not very desirable in training because, again, getting sample coverage in a high dimensional space is quite challenging. So you need rather large batches to get meaningful comparisons. So what we're going to do often is down select in 2 different ways. Delta T here that I'm mentioning doesn't necessarily have to be the time step of the M-step generator. This could be much larger time steps so that you're only sampling at select times, and that way you can get sensitivity to the dynamic responses on large time scales, but the underlying numerics is using a much smaller sub-step. And so that's the strategy we'll typically use with these full trajectory approaches. And that's what's being denoted here by this tau that you're seeing there. And so the conditional methods, as the name implies, this will be where we'll use trajectory fragments. This would be most appropriate where we're able to generate entries of the training set from something like a high fidelity simulation. So these would start off with like the same local initial conditions and then evolve for some period of time. It's kind of like a little local burst, if you like, of trajectories. And then, of course, you're learning these probability distributions, which are conditionals, on those different samples for the initial conditions. And that has obviously training benefits, again, if you have some control over initializing the training set data. And then the marginals don't require that. The marginals simply just take a fragment of the trajectories, and essentially you're just trying to learn marginal distributions for some specified ranges. You can either do it as kind of like a sliding window, or you could have it at one specific time. So the main point I really want to make is there's all kinds of interesting variations and combinations of what I've specified here that can be used to greatly improve potentially training when you're trying to learn these stochastic dynamical models. And so I'll focus on these kind of three standard cases. All right, so for the generator loss, I'm going to reformulate it so I'm not simply using a 0-1 classifier. And this is with the objective of trying to get a little bit more information about the dynamical trajectories that can be used as a learning signal in the gradient of the generator. And so what I'm going to do is, instead of using just a sort of binary classifier, I'm instead going to learn a critic or a discriminator that is essentially a function which is going to aim to distinguish between the two probability distributions. So you can think about this function as basically being like a signature that tells me how different these two random variables are, where the function is restricted to come from some range of features or functional forms. And I'll get into that in more detail from the probability and statistics literature. This is what's known as an integral probability metric. Depending on how you choose this model class fancy F here, you can get all kinds of interesting metrics, including the Kantorovic's metric associated with optimal transport, like the Wasserstein metric, for example. That would be the one Lipschitz functions for Lipschitz constant less than or equal to 1. You can make other choices to get other well-known metrics and divergences. The choice that we're going to make here, and again, the whole purpose of this is to compare the empirical distribution of the generator and the training set. We're going to use a reproducing kernel Hilbert space for F here, and we'll look at all of the functions that have norm in that space less than or equal to 1. So there's a number of nice things that happen if we use that. Depending on our choice of kernel, this, of course, can give us rather rich ability to distinguish between probability distributions, while at the same time having some other structure which we can utilize for the purposes of training from these finite sample sets. A lot of what will happen here is it'll be similar to doing something like a kernel density estimate of the two distributions and kind of comparing their difference. But of course, what kernel you choose will affect what's being emphasized in those comparisons. So the key property that I'm going to use for that kernel, for now, I'll just leave the kernel generic, and I'll say a little bit more about what we use when I get into the examples, is we'll use the fact that if we're in a reproducing kernel Hilbert space, then we can evaluate the function f at a particular value x by simply taking the inner product of f with the kernel. Now, using that property, if I substitute that in above here, it actually can be, I can simplify the form of this optimization problem that I need to solve. I'll use the notation mu p. You can think about this as an embedding of the first probability distribution, and mu q as an embedding of the second probability distribution into the reproducing kernel Hilbert space. I can use that along with this kernel property to basically commute the inner product with the expectation. And if I do that, then this integral probability metric that I get can be expressed in this form. This is what's known as maximum mean discrepancy. And you can see readily now that optimizing over all norm 1 functions would be given by simply taking the direction of that second vector or that second function, and that's simply given by the difference between the embeddings over the norm of the embeddings. And so when you work it all out, again, going back and using this property of kernels, you can express this as the sum of kernel expectations. Now, all that looks great. The one drawback, of course, of this is that these are second-order statistics, and we'll talk about how we'll deal with that in a little bit. And so this provides us then, from the sample-based point of view, this would provide us with a loss function for our generator. In particular, we can take this expectation quantity, let's just square it to get rid of the square root, since at the end of the day, we're interested in doing optimization, minimizing. And then we can use this unbiased estimator here, which would then give us a sample-based estimate of the MMD. And so that's what we're going to use for our generator loss. This is basically a way of determining the discriminator analytically, so I don't have to go through a separate training or optimization problem like I did in the standard GANs formulation. And so now that takes the discriminator optimization part out of the problem, and now I can focus on simply minimizing the objective for the implicit generator. And so that'll boil down to this loss function, which I'm showing here, which will amount to essentially the empirical estimator for the MMD that I'm showing in the upper right. And this is just computing MMD, the unbiased estimator, for effectively those empirical distributions of G and D. All right, so that's going to be the overall loss that I'm going to use in my generative formulation. And now it boils down to how do I actually compute this in practice for performing training using things like stochastic gradient descent. And so what's really crucial here is that I be able to compute gradients of that loss function efficiently. And it turns out that if I use just standard backpropagation methods, the computational call graphs should become prohibitively large for backprop. So I'm going to make use of more mathematical structure of this loss function. And so the first observation is just to note that we have to do these double sums over the samples, not very computationally efficient, again, if we were to use sort of direct backprop on the computed expressions. But we have a lot of probabilistic dependence here that we know in advance. We know that the sample points, for example, come from those m-step updates. We know a lot about the structure of the objective function coming from the kernel evaluations that I showed you before. And so, again, high dimensions, having to deal with these second-order statistics, and that's what I'm going to address next. So the basic approach that we're going to take is closely related to adjoint methods, and we're going to use that in a judicious way, both for computing aspects of the second-order statistics as well as the dependence on the stochastic trajectories. And in this way, then we'll have a viable training protocol for learning over those m-step methods with these MMD losses. So just to give a quick overview of those techniques, what we're doing is we're ultimately trying to compute gradients of an expectation. And so the way that we'll look at this from a mathematical perspective is we'll build all of the dependencies into the parameters p that we're trying to learn into the random variable. So we'll assume there's some base measure. I'll call that omega. You can view then the expectation. In our case, it's the MMD that we're taking expectations of. The stochastic trajectories are being generated by an implicit generator that has some parameters p. So the random variable is what has the p dependence, not the base measure. And in that case, then we can commute taking gradients in the expected quantity with taking expectations of the gradient of the random variable, essentially. And so that's just the key assumption that we're going to make in our notation, essentially, or formulation. And of course, what we're doing here is a discrete approximation of that expectation, and it follows, as I've shown here on the right, to effectively being able to compute gradients of the sample terms. Okay, so now if you look at the gradients of the sample terms, the problematic part is having to create gradients in the stochastic trajectory components. And if you were to go through again and kind of do this in a straightforward way using the chain rule, this becomes rather expensive because you would compute gradients in all the different stochastic trajectories and then ultimately contract them with these partials x and phi. And so it turns out, and this is an insight that's used in adjoint approaches in control theory and other areas, it turns out that because you're doing this contraction, there's actually an alternative formulation of the contribution of this term, and I'll walk you through how that plays out in the context of our methods. So the challenge is to compute efficiently the contributions of those gradients in P of the sample set. So as you adjust the parameters of the stochastic model, right, that's going to affect all of the samples that are produced, and that's what we need to deal with. So the alternative approach that we're going to take is going to be based on an adjoint formulation, and really what we're going to utilize is the fact that if you look at the solution to that m-step method, you see that it solves this implicit equation here. And so where f has these components, and if we do that, this implicit formulation allows us to utilize the implicit function theorem, which basically says that if we take a derivative in the parameters, we can express it in this way using the total derivative, and we can actually solve for xp in terms of derivatives of f. So we've kind of shifted everything off to the implicit function f instead of having to compute in terms of xp directly. And that has a bunch of nice properties, as you'll see, because now what I can do is I can contract this expression quite readily, and often I'll get a problem that's much easier to solve than if I had constructed all of those explicit gradients. All right, so then xp can be expressed in terms of the Jacobian in this way in terms of derivatives of the implicit function f. All right, so I've just copied that over here on the left, and the adjoint approach is to compute then the full derivative by plugging in this expression for xp and then just rearranging the order in which you're going to do the contractions. And if you do that, then you can show that this whole expression will boil down to essentially contracting a vector r with fp, where r satisfies this equation. So the real challenge then, I would say, is to come up with an efficient way to compute each of the steps in this gradient computation, which is to compute gx, fx, that gets you the Jacobian, have an efficient solver for r, then compute GP, FP, and then now you get your full gradient through combining those terms with that solution r. It's really the computation of r that's typically the part that could get computationally expensive. I'll show you in the context of these m-step methods, we actually can get very efficient algorithms. In fact, a solver which amounts to solving a system of recurrence equations to construct that vector. All right, so that's the objective. And then all that will be used to compute the gradients of these empirical estimators of the expectation. All right, so just to get through that, the second order statistics, I don't want to say too much about that. You can basically use the chain rule. And again, if you judiciously look at what you get, it turns out that you can reduce things to essentially doing an adjoint method on this linear function. I won't say very much about it, but you can use the technique that I've showed you on the previous slide to construct then derivatives of the overarching loss. So the real challenge then comes up to having effective adjoint methods for the stochastic trajectories. And so I'll focus on that just in the interest of time. And so up there on the upper left is the gradient method. This is the implicit formulation, including the initial conditions. I'll go through this rather quick because I do want to have sufficient time to talk about results. You can look in our paper for a lot of the details, but just some notation, FJD will be the implicit equation for the jth step and dth component. And then when I take a derivative, I'll just put that second index there. So putting all these pieces together, what you basically have to compute is for these implicit equations, you have to compute the following Jacobian. That's done rather straightforwardly using these FJD, FKD prime terms. And you take the transpose. This gives you a set of linear systems. I'm going to break the R vector down into components corresponding to the steps at the end of the trajectory all the way back to the beginning. So what I'm really utilizing here is that probabilistic dependency that I have, in particular the form of these updates. And so if I do that, I can first compute Rn, then use that to compute Rn minus 1 all the way down to R0. Put all those together, composite, that will get me R, and I can use that in my gradient calculation to get the update. So that's the strategy here. I realize I'm going a little quick, but I just, in the interest of time, want to go through this briefly, and I'll refer you to the paper for a more in-depth discussion. So at the end step, you basically have this particular equation for the Rn components. You can solve that outright in terms of derivatives of phi. Now you have that. If you go to step n minus 1, n minus 2, and so on back, you can again solve directly for RKD. You put everything here on the right-hand side. Notice those indexes are +1 plus L, so you have those in hand from the previous step. And then, of course, if you're more than m steps away from the end point, then you get this generic formula that, again, allows you to solve for RK in terms of the previous iterates that you already have in hand. So this gives you a very efficient solver now to get R, and that's sort of the key component in our gradient calculations for doing stochastic gradient descent of this generative modeling approach. All right, I'll refer you to the papers again for details there. And I've already said a lot about the training protocols, and these can be obviously adapted and applied quite readily within each of these contexts. All right, so let me in the remaining time just talk a bit about some of our early results with these methods. As I mentioned, it's pretty recent and ongoing work. So the first problem I mentioned was learning parameters of mechanical systems. And in particular, I'm going to look over the model class of Langevin dynamics. These will be inertial Ornstein-Uhlenbeck processes. So you can think about that bead spring system. And the objective here is from observations of the trajectories, essentially to learn the stiffness, damping, and fluctuation related terms. And I'd like to do that simultaneously using this generative approach. The challenge, of course, with that is dimensionality. These are basically what the observables are. I don't have a lot of time to go into detail here, but you can see that there are different time scales at which those different parameters are sensitive. And that does play a role in how you ultimately formulate those training protocols that I was referring to. And I'll refer to the paper again for some more in-depth discussion of that and be happy to talk offline. So I just want to point that out qualitatively. You see that. The way that'll manifest is when we're observing and doing our training, if we use, for example, the conditionals and the marginal distributions, we're essentially training over observations that are analogous to what I'm showing here on the right. All of this is done for a three-dimensional system. We're using rational quadratic kernels, I should mention. And there's an important role that this timescale tau that we subsample on plays in the training protocols. So here's some quantitative results. I'll just start with the stiffness. You can see as we vary tau, we're able to get this quite accurately estimated. We estimated stiffness, temperature, damping simultaneously. Something interesting happens in the training in that, just like with maximum likelihood estimation, there's a tendency to get pulled towards a local minimizer, where if you make the temperature very large, of course, that will make the training data quite plausible under your model, but in a suboptimal sense. One of the nice things about the MMD that we noticed is that once the stiffness seems to get within the right ballpark, it gets pulled away from that kind of local minimizer towards then the correct temperatures you're seeing here in this particular training run, and similarly with the damping. So you can see that there's also interesting sensitivity on the time scales here, and just comparing the different protocols, full, conditional, marginals, for a relatively large sampling time scale versus a small sampling time scale. You can see that that plays a significant role in the accuracy of the results, especially when we look at something like the conditionals. We get very good accuracy for large time scales because there's sufficient sensitivity to stiffness, whereas as we go to very small time scales, essentially that learning signal that you would get for determining the stiffness parameter is getting washed out by other things like the thermal fluctuations and the damping. So these are important hyperparameters to keep in mind when training on these stochastic systems. This just shows we get a very accurate result for stiffness. We similarly did a study with temperature. This is all the parameters are trained simultaneously. We're finding temperature is a much more challenging term to pin down in detail, partly because it can make up some of the discrepancy between the models by simply increasing the noise. So if we don't have perfect overlap between the training samples and the generated samples, it can kind of make those things line up and agree. So it might be picking up simply on the sampling error, and that's something we're currently investigating. For many training runs, we'll see the behavior that you're seeing in terms of epochs here, but for some of them, they fail for the reasons that I alluded to. Similarly, we can estimate the damping parameter, and again, you see some sensitivity there on the timescales at which the dynamics are probed. And so we see in each case different pros and cons to those different training protocols, but the SDE-GANs, you can mix and match or choose between those approaches as well as tuning that timescale tau. This is just showing real quickly some results for learning models where there's unknown force laws. And so in this case, we have observations of a particle system, and we're going to learn over the modeling class of, again, inertial Langevin dynamics. And really the objective here is to learn neural network representation for the unknown force law. Here, I'll assume for now in this study that the damping and the thermal parameters are known, but you also could try to learn those simultaneously as well. But again, you have that challenge of these very sort of high-dimensional probability spaces, but that graphical model structure will be utilized to exploit those dependencies. So here on the left is showing the kinds of observations we have, obviously many more than just these 3 or 4 samples, but just to show you what the data sets look like that we're training from, essentially an ensemble of trajectories of that nature, you'd be learning from observing those dynamics. On the right is learning over trajectory fragments. We do that with the conditional and the marginals. So this is just showing some results. This is the case of we're doing a radial symmetric double well potential. This is showing the force law that we're targeting. We're using a neural network representation for this neural network. So we're training, again, using the custom backpropagation approaches I showed before. And this is showing the model that we learned. And really, I think the advantage of these approaches is that we're not reliant on things like the system having equilibrated, which would be required for techniques that make use of sort of a priori knowledge of the marginals. We also can deal with systems that are potentially not in equilibrium, because the primary driver of the statistics that we're trying to align are the intrinsic Langevin dynamics. And so on the right is just showing training the double well potential. And then the way we're going to characterize this is in terms of the L1 error of the radial distribution function. This is not something that was used in the training, but just to have reliable test errors, which would govern a lot of the statistics ultimately of that model that you've learned. And I'll just show some quick results for that. This is just showing on the left the learned model. So you can see that we get viable long time simulators. And on the right is showing the training data set. And then this is just showing some quantitative results. And again, we did some studies as we varied the temporal sampling parameter. So I won't go into a lot of detail there, but just to show that, yeah, we're able to learn nonlinear force laws. And we're kind of pushing this in a number of directions to improve both the dimensionality and the complexity of the problems that we can deal with. But I hope this gives kind of a proof of concept of some of the recent work that we've been doing. And I'd be happy to talk more about that offline. I'll refer you to the papers. So thanks again for having me. Look forward to continuing discussions.